There is an object in the sky tonight that most people have been taught to think of as beautiful. A soft, pale smudge in the constellation Andromeda, visible to the naked eye from any reasonably dark place on Earth. Astronomers have photographed it 1,000,000 times. Textbooks have printed it 1,000,000 times more. And every single one of those images is misleading. Because what you are actually looking at is not a distant, drifting neighbor. It is the leading edge of the largest structure in our part of the universe, closing on us at 250,000 miles per hour. Its outer envelope is already touching ours. And what is coming toward the Milky Way is not a galaxy in the way you have been trained to picture the word. It is something much worse. And by the end of this, you will not use the word merger the same way again. Now, before I go any further, where are you watching this from? Because whatever hemisphere you are in right now, that pale smudge is somewhere in your sky, closer than it was yesterday. Take a second and sit with that. Here is the thesis, and I want to plant it now, at the top, so that everything that follows lands correctly. The public story about Andromeda is that in roughly 4.5 billion years, our galaxy and its neighbor will slowly, gently combine into a larger, more magnificent galaxy. That story is not exactly a lie. It is a carefully softened version of what the physics actually describes. And once you look at the real numbers, the real mass, the real halo, the real velocity, the real dynamics of what happens when two galactic-scale gravitational wells interpenetrate, the softened version starts to look like a press release designed for calm, not for accuracy. The first thing you have to understand is that the picture you have in your head is wrong at the level of scale. You have seen photographs of Andromeda as a bright spiral roughly 6 times the width of the full moon in the night sky. That figure is real. It comes from long exposure imaging that captures the visible stars. But those visible stars are only the innermost, brightest part of the galaxy. In 2020, a Hubble project called Omega, absorption maps in the gas of Andromeda, traced the true gaseous halo of the galaxy out to a distance of roughly 2 million light-years. That is not a typo. 2 million light-years. Which happens to be almost exactly the distance between Andromeda and us. Do you see the problem? If Andromeda's halo extends 2 million light-years, and the distance between us is roughly 2.5 million light-years, and our own halo extends outward on a similar scale, then the two halos are not separated. They are already in contact. Right now. Tonight. The collision the headlines describe as 4.5 billion years away started at the halo level some time ago, and no one told you. If we could see that halo, if our eyes were tuned to the ultraviolet absorption signatures Hubble uses to map it, Andromeda would appear as an object roughly 6 times wider than the full moon every night, painted across a huge fraction of the sky. It would not look distant. It would look like weather. It would look like a thing arriving. This is the part that should bother you. The gap between what Andromeda looks like in a photograph and what it actually is, physically, is one of the largest perceptual mismatches in modern astronomy. And the mismatch was not created by scientists. The papers describe the halo. The papers describe the velocity. The papers describe the dark matter mass. The mismatch was created by the summary, by the digestible, reassuring wonder-first version that gets translated into press releases and headlines and Instagram captions about how gently our galaxies will one day meet. Let me give you the numbers plainly, and then translate them into something you can feel. Andromeda is approaching us at roughly 110 kilometers per second. That is about 68 miles per second, which is about 250,000 miles per hour, which is fast enough to cross the diameter of the Earth in 1/3 of a minute. It is not drifting toward us, it is falling toward us under gravity, gaining speed. And the mass doing the falling is enormous, around 1.5 trillion times the mass of our Sun, most of it invisible. Now think about what that means. When you look up at that faint smudge on a dark night, you are looking at a gravitational structure whose visible portion is a small fraction of its total influence, whose outer boundary is already touching us, and whose center is closing on our center at more than 250,000 miles per hour. That is not a peaceful sky. That is not a stable neighborhood. That is the visual signature of a slow-motion galactic collision already underway. And here is where I want you to strip away one particular piece of comfort. The phrase you have heard most often, that no two stars will collide because space is so empty, is true. It is also almost entirely irrelevant to what will actually happen. Stellar collisions are not the mechanism of galactic mergers. Gravity is. And gravity does not need stars to touch in order to destroy the structure that holds them in place. By the time we finish this story, you will understand that what is coming is not a merger in any meaningful sense of the word. It is a disruption. It is the end of the Milky Way as a coherent object, and the end of Andromeda as a coherent object, and the birth of something neither of them chose to be. And it is not 4.5 billion years away. It is happening, right now, at the edges, in the halos, in the numbers that have been quietly updated in the papers, while the summaries stayed the same. Stay with me, because the deeper you go into the actual physics, the harder it becomes to unsee what the headlines have been softening for decades. Let's start with what you have most likely been told. In 2012, NASA released one of the most widely circulated astronomical statements of the last 20 years. Using Hubble Space Telescope measurements of Andromeda's motion, a team predicted that in about 4.5 billion years, our galaxy and Andromeda would collide. The press release emphasized three things. First, the collision was a very long way off. Second, no stars would physically strike each other because the distances between stars are so vast. Third, the eventual outcome would be a larger combined galaxy, casually nicknamed Milky, a friendly, almost affectionate word designed to make the event sound like a slow dance rather than a crash. That framing traveled. It became the standard summary in documentaries, school textbooks, YouTube explainers, and casual dinner party astronomy. And there is a reason it traveled. It is emotionally digestible. It is technically defensible. It contains no obvious falsehood. But it does something specific with the truth. It selects the softest interpretation of a set of facts that also permits much harsher interpretations, and it presents that softest interpretation as if it were the only one. Look at what the standard version emphasizes. The timeline is 4.5 billion years. The mechanism is described as gentle. The outcome is described as combination. The individual scale, no stars will collide, is used to imply that the systemic scale will also be safe. Now look at what the standard version omits. It does not tell you that the halos are already in contact. It does not tell you that Gaia data, released after that 2012 press release, changed the geometry of the predicted collision. It does not tell you that the resulting object is not a spiral galaxy at all, but a featureless elliptical, which is what you get when you destroy two spirals. It does not tell you that Milky is a cute word for the corpse. Let me take the second point seriously, because it matters. In 2019, using data from the European Space Agency's Gaia mission, astronomers updated the measurement of Andromeda's transverse motion, the sideways component of its velocity as opposed to the head-on approach. The updated numbers suggested that the collision would not be a direct central impact, but something closer to a violent grazing encounter, in which the two galaxies would swing past each other, tear each other into long tidal streams, fall back together, and eventually merge on a second pass. That is not a merger. That is a two-stage disassembly. This is where the reassuring frame starts to leak. Because a grazing pass followed by re-collision is a specific dynamical process astronomers have watched happen elsewhere in the universe. It is not gentle. It is not clean. It leaves behind an object that no longer resembles either progenitor. The spiral arms, the beautiful familiar arms of both galaxies, do not survive. They get flung outward, thinned, dissolved. Star formation regions get compressed and detonated into supernova cascades. The disks lose their rotation. The bulges swell. What remains, hundreds of millions of years later, is a smooth, roughly spherical, dynamically hot, elliptical galaxy. A shape astronomers associate specifically with the end products of major mergers. Now think about what that means for the sky. Every human being who has ever lived has looked up at a night sky organized around the band of the Milky Way. Every constellation you have been taught, every mythology, every cave painting of stars, every navigational tradition, all of it built on the assumption that this pattern is permanent. It is not. In the long timeline, the band goes away. The disk we live in stops being a disk, and the sky your descendants would see, if any of them survive that long in some form, is not the sky humanity has always known. That, by itself, is not the horror. Timelines that long are hard to feel. The horror is smaller and more immediate. It is that the story you have been told about this process, the story of gentle combination, of no consequences, of two galaxies politely merging into a bigger one, is not what the physics describes. It is what the physics gets translated into after several rounds of institutional softening. And here is where the first crack in the public story becomes structural. If the timeline is 4.5 billion years and the mechanism is now understood to involve a grazing pass and a re-collision, and the outcome is the destruction of both spiral structures, then the phrase "no stars will collide" is not a comforting fact. It is a distraction. It is technically true and topically irrelevant. It answers a question no one should have been asking in the first place. The question is not whether individual stars will touch. The question is what happens to the gravitational architecture that holds solar systems in orbit for billions of years. The question is what happens to the gas clouds where new stars form. The question is what happens to the two supermassive black holes at the two centers when they finally begin to orbit each other. The question is what happens to a star like ours sitting on the edge of a spiral arm when the spiral arm itself stops being a stable feature. None of those questions can be answered by pointing out that space is empty. Space is empty at the scale of stars. Space is not empty at the scale of gravity. This is where the merger stops being the least interesting thing about Andromeda. Because if you have already accepted that the public story is a softened version, then you have already accepted that there is a harder version underneath. And the harder version begins with a fact the summaries almost never mention. Most of Andromeda is not stars at all. Most of Andromeda is invisible. And that invisible portion is the part actually deciding what happens to us. To understand what Andromeda actually is, you have to stop thinking of it as a collection of stars. Stars are what you see. They are not what matters. If you added up every star in Andromeda, roughly 1 trillion of them, more than double the star count of the Milky Way, you would still be counting only about 15% of the galaxy's total mass. The rest, the other 85%, is dark matter. And dark matter is what is going to hit us first. Picture an iceberg. You have seen the standard illustration 100 times. A small white peak above the water and a much larger dark mass hanging below. Andromeda is an iceberg. Every photograph you have ever seen of it, every long exposure image showing that graceful spiral with its two smaller companion galaxies, is the 15% above the waterline. The rest of the object is beneath the surface of your instruments, invisible to every telescope humanity has ever built, and it is that invisible mass that will decide the geometry of the collision, the timing of the merger, and the fate of the two galactic disks. Let me put that in numbers you can carry. The total mass of Andromeda is estimated at around 1.5 trillion times the mass of our Sun. The Milky Way is roughly comparable, depending on the model, somewhere between about 1 and 2 trillion solar masses. Together, we are looking at a combined gravitational structure of around 3 trillion solar masses, most of it dark, most of it currently unmapped, most of it in motion toward a single common center of mass located in the space between us. That is the real object, not the pretty spiral. The pretty spiral is jewelry on a bulldozer, and here is the historical part that I think is the most humbling. In the 1920s, when Edwin Hubble was measuring the distances to what were then called spiral nebulae, the scientific consensus was that Andromeda was inside our own galaxy, a cloud of gas among the local stars. Hubble proved otherwise. He showed that Andromeda was a separate galactic system, at a distance so enormous that it broke the previous conception of the universe entirely. That was 100 years ago. In 1 century, our understanding of what Andromeda is has expanded from a cloud within our galaxy to a separate galaxy, to a galaxy with a massive dark halo, to the dominant gravitational partner in our local group already interacting with us. Every one of those expansions made Andromeda bigger, closer, and more consequential than the previous generation of astronomers thought. Every one. And the current generation, the Hubble Fat Survey, the Omega absorption maps, the Gaia astrometry, is still expanding it. If you look at the trend line of our own updates, we have never once revised Andromeda toward being smaller, more distant, or less involved with us. Every revision goes the other way. That is a pattern worth pausing on. Because science, when it is working well, corrects in both directions. Some things turn out smaller than we thought. Some things turn out larger. But Andromeda has only ever turned out larger, which means the current numbers are, statistically speaking, more likely to be underestimates than overestimates, which means the current predictions of when and how the collision unfolds are probably conservative. Now let me connect that to something that should bother you. The famous 4.5 billion year timeline is based on gravitational modeling of the visible masses of the two galaxies and the best current estimates of the dark matter halos. If those halo estimates are conservative, and every trend suggests they are, then the actual timeline for meaningful gravitational interaction is shorter. Not by billions of years, but by hundreds of millions potentially. Which sounds like a lot, until you remember that we are talking about a system that has been evolving for over 13 billion years already. Here is the deeper problem though. The timeline is a summary statistic. It is the year when the two galactic centers pass close enough for the merger to be considered underway. It is not the year when Andromeda starts affecting us. Because in a system dominated by dark matter, the influence begins wherever the halos overlap. And the halos overlap now, which is the moment I want you to fully absorb. The 4.5 billion year figure is the estimated time until the two visible galaxies begin to interpenetrate at the disk level. It is not the beginning of the interaction. The interaction has already begun. It is happening in the gas. The diffuse, ionized gas at temperatures of hundreds of thousands of degrees that surrounds each galaxy. That gas is where the dark halos are traced. And that gas has been sloshing between our two systems for hundreds of millions of years already. Some of it, according to recent models, may have already been exchanged. Think about what that phrase means. Some of the matter now in the Milky Way's halo may have originated in Andromeda. Some of the matter now in Andromeda's halo may have originated in the Milky Way. The two galaxies have already been trading pieces of themselves for a geological timescale, and no one told you, which means the timeline is, in a sense, a rhetorical convenience. The moment when the impact becomes visible in a telescope is not the moment when the impact begins. The impact began before humanity existed. It has been getting slowly worse the entire time, and it will get worse from here. This is the point where the physics stops being reassuring, if you were still holding out hope that it might be. Because if most of Andromeda is invisible, and if the invisible part is already here, and if our models of that invisible part have only ever grown larger and more consequential, then the timeline every documentary quotes is built on the fraction of the problem we can measure. The rest is arriving on a schedule we cannot yet see, and that rest is where the actual danger lives. Here is a fact that will probably feel wrong the first time you hear it. A galaxy is not an object. It is not solid. It is not held together by anything like the forces that hold together the things you interact with every day. It is not a coherent body in the sense that a planet is a coherent body or a star is a coherent body. A galaxy is a negotiation. It is a delicate, continuous, dynamic balance between gravity pulling inward, angular momentum resisting collapse, gas pressure supporting the disk, and dark matter shaping the whole envelope. That balance is what holds a spiral in the shape you recognize. And a major merger breaks that balance in every possible direction at once. Let me walk you through the specific failure modes, because they are not intuitive, and each one matters. The first is tidal disruption. When two galaxies pass close to each other, the difference in gravitational pull across the width of each galaxy, the tidal force, is enormous. Stars on the outer edges feel a very different gravitational pull than stars near the center. The result is that outer stars get flung outward, sometimes into long, glowing tails that stream across the space between the two galaxies for millions of light years.
Astronomers see these tidal tails everywhere in the universe, in every galactic pair caught mid-collision, the antennae galaxies, the mice, NGC 4676. In every single case, the outer stars, the ones on the fringes of each spiral, are the first to go. Our sun is on the outer edge of the Milky Way, not the very fringe, but well outside the central bulge. When the tidal forces of the merger arrive, stars in our neighborhood are among the ones most likely to be gravitationally reshuffled.
Some estimates, based on simulations, suggest that our solar system has roughly a 12% chance of being ejected from the merged galaxy entirely, flung outward into the intergalactic dark, no longer bound to any spiral, no longer surrounded by other stars in any recognizable pattern. Think about what that would look like. Not that it would happen quickly, nothing at galactic scale happens quickly, but over hundreds of millions of years, our night sky would grow emptier, not fuller, emptier. The familiar band of the Milky Way would fray and fade. The stars would spread out. The universe outside our system would go dark in a way it has never been dark in the entire span of biological evolution. That is one possibility. And a 12% probability is not small. The second failure mode is gas cloud compression. Galaxies are not just stars and dark matter. They are also enormous reservoirs of cold molecular hydrogen, the raw material of new stars. When two galaxies collide, those gas reservoirs get slammed together at high velocity, compressed, and detonated into rapid, violent bursts of star formation. Astronomers call this a starburst. In a starburst galaxy, the rate of new star formation can be 10 to 100 times higher than in a quiet spiral like ours. And when you form that many new stars quickly, you also produce, a few million years later, a wave of supernova. The most massive stars burn through their fuel first, and they end in explosions that can outshine an entire galaxy for a brief moment. During a merger-driven starburst, the supernova rate rises dramatically, potentially from about 1 per century in the current Milky Way to something like 10 or 100 per century in the merged system. The third failure mode is the black holes. The Milky Way's central supermassive black hole, Sagittarius A, weighs about 4 million solar masses. Andromeda's central black hole is estimated at more than 100 million solar masses. During the merger, these two objects will not immediately combine. They will spiral toward each other slowly, over tens of millions of years, radiating gravitational waves, the same kind of waves LIGO detects from smaller black hole mergers, except vastly more powerful. As they spiral in, they will drag matter with them. Stars that happen to pass too close will be tidally shredded. Gas will fall into accretion disks around each black hole, and each disk will radiate enormous amounts of energy, X-rays, gamma rays, ultraviolet, into the surrounding galactic volume. And this is where I need you to hold two things at once. First, the specific failure modes I just described. Tidal disruption, starburst supernovae, black hole coalescence, are not speculative. They are observed in real galactic collisions elsewhere in the universe, right now, and we can measure their consequences directly. Second, all of them will happen in our merger. Not maybe, not depending, all three. The only questions are timing, intensity, and how close our solar system happens to be when they occur. That is what I mean when I say a galaxy is not an object. It is a negotiation. And the negotiation ends when the merger arrives. What you get afterward is not a bigger version of the Milky Way. What you get is a physically different kind of galaxy, an elliptical, hotter, less structured, with disrupted gas dynamics, an active central region, and no coherent disk. A galaxy in the shape of the collision that made it, rather than the shape of the systems that preceded it. And here is the cliff. The ejection scenario, the 12% chance that our solar system gets flung into intergalactic space, sounds like the worst outcome. It is not.
because being ejected means being taken away from the disturbance. Being ejected means going somewhere quiet. The worst outcome and the more probable outcome is the opposite.
It is being pulled inward, closer to the merging central regions, closer to the black holes, closer to the starburst, closer to the radiation. The worst version of the merger is not exile. It is proximity. And that possibility, statistically, is much more likely than escape, which means the median outcome for our solar system during the merger is not being flung to safety. It is being drawn deeper into the storm. Now, I want to attack an assumption that is buried so deep in the way we talk about the merger that most people never notice they are making it. The assumption is that a bigger collision is just a proportionally bigger version of a smaller one. That if you take a small galactic encounter and scale it up to two large galaxies, you get a bigger, but essentially similar event. That intuition is wrong. And it is the kind of wrong that hides the actual danger. When two galaxies interpenetrate, the danger does not scale linearly. It scales with how many other structures the merger disturbs. And the number of structures being disturbed grows faster than the mass of the galaxies involved. Two galaxies passing through each other is not two objects colliding. It is billions of stars, each with its own orbital path, each with its own history of gravitational interaction, being simultaneously renegotiated in a chaotic gravitational field. Every star's orbit gets nudged. Every gas cloud gets compressed. Every dormant black hole gets fed. Every stable region becomes less stable. Let me put this in concrete terms. The current Milky Way experiences roughly one supernova per century on average. That is the baseline rate for a quiet, well-behaved spiral galaxy going through normal star formation. During a merger-driven starburst, that rate can rise by an order of magnitude or more, 10 times more, potentially 100 times more, which means, at peak, one supernova per year in the merged galaxy, perhaps more, for hundreds of millions of years. Now let me translate that into something you can feel. A supernova is not just a bright star. It is a stellar detonation that releases in a few seconds more energy than the sun will emit in its entire 10 billion year life. The shockwave carries with it a burst of high-energy radiation, X-rays, gamma rays, cosmic rays, that spreads outward at nearly the speed of light. If a supernova occurs within roughly 30 light-years of an Earth-like planet, current models suggest it can strip a significant fraction of the planet's ozone layer, dramatically increasing the ultraviolet radiation reaching the surface. Some biologists have argued that a nearby supernova may have contributed to at least one of Earth's minor mass extinctions in the deep past. The Milky Way's current supernova rate makes such a close event rare. Very rare. Perhaps once every few 100 million years, on average, we get a supernova close enough to matter biologically. During the merger-driven starburst phase, that rate could rise by a factor of 10 to 100, which means what was once a several 100 million year event becomes something closer to a few million year event, which means Earth, or whatever planet our star still happens to have at that point, becomes vastly more likely to be inside the danger zone of at least one nearby stellar explosion during the merger. This is what scale rupture looks like. You cannot simply say the merger is twice as dangerous because there are twice as many stars. The danger multiplies because it depends on how many potentially catastrophic events are packed into a given volume of space and a given span of time. And a starburst galaxy is a place where the density of catastrophic events per unit time is dramatically higher than in a quiet spiral. We can watch this happen elsewhere, right now. The antennae galaxies, about 45 million light-years away, are a real, ongoing collision between two spirals that started their merger a few 100 million years ago. Astronomers have imaged them in exquisite detail with Hubble and later with James Webb. What we see is exactly what the theory predicts. Huge tidal tails streaming outward for hundreds of thousands of light-years. Massive starburst regions glowing pink and blue in the compressed gas. Supernova remnants scattered across the collision zone. Two central regions that are still separate, but slowly spiraling toward each other. The antennae are not a simulation. They are a preview. The mice galaxies. NGC 2623, ARP 220. Every major merger we can observe shows the same features. Tidal disruption, starburst, elevated supernova rate, active galactic nucleus development. In every case, what emerges from the collision is not a scaled-up spiral. It is a fundamentally different kind of galaxy, shaped by processes that a quiet spiral never has to survive. And here is what I want you to hold on to. Every one of those observed collisions is what our merger will look like from the outside to any astronomer in the universe watching it happen. The Milky Way-Andromeda merger, viewed from 100 million light-years away, would appear exactly like the antennae: messy tidal streams, bright compressed cores, elevated brightness in the starburst regions. The images we take of distant collisions are in effect photographs of our own future, which raises a question that most people never think to ask. If we can see, right now, in detail, what a merger of two spiral galaxies looks like, and if we know from those observations that the process involves tidal disruption, starburst supernova, black hole coalescence, and the destruction of the disk structure, then why is the public story of the Milky Way-Andromeda merger so much gentler than the actual observed evidence? The answer, I think, is partly that 4.5 billion years feels safely distant, and partly that no stars will collide is a rhetorical layup that ends the conversation before the harder questions get asked. But the observed evidence is not gentle. The observed evidence, in every real merger we can see, is violent, prolonged, and destructive of the original galactic structures. And there is no reason to think our merger will be any different. So the question I want you to sit with is not whether Earth survives the merger. Earth is a rock. Rocks are hard to destroy. The question is what happens to the thin envelope of atmosphere, magnetic field, and biosphere that we depend on. That envelope is not a rock. That envelope is fragile. And the merger, at its peak, is the kind of process that erodes fragile envelopes. Not in seconds, not in years, but in the geological rhythms that biospheres actually live and die by. Let's move from stars and galaxies down to something you can actually feel. Skin, cells, DNA, ozone. The thin, invisible things that let a rock like Earth grow forests instead of remaining a sterile ball of stone. Because long before any hypothetical star collides with our sun, the merger is going to affect the environment our biology depends on, and the effect is not subtle if you look at it carefully. Start with the black holes. Right now, Sagittarius A, the black hole at the center of our galaxy, is quiet. It sits there, 4 million solar masses of compressed gravity, doing almost nothing. It occasionally consumes a small amount of infalling gas, produces a modest amount of X-ray radiation, and otherwise stays out of our lives. That quiet is not a permanent feature. It is a temporary condition, dependent on the fact that not much material is currently being funneled toward the galactic center. During a major merger, that changes. When two galaxies collide, gas clouds get compressed, angular momentum gets disrupted, and the central regions of each galaxy suddenly become much better at feeding their central black holes. Astronomers call the result an active galactic nucleus, or AGN. An AGN is what a supermassive black hole looks like when it is actively consuming matter. It is one of the most energetic phenomena in the universe. A single active galactic nucleus can outshine an entire galaxy of stars. It emits enormous quantities of X-rays, ultraviolet radiation, and high-energy particles. And it does so continuously, sometimes for tens of millions of years. If our merger activates either Sagittarius AE or Andromeda's central black hole, or both, which is what most models predict, the merged galaxy will spend a significant fraction of its early history bathed in high-energy radiation from its own core. Every star in the galaxy, including any planetary system nearby, will experience an elevated background of ionizing radiation. Not enough to sterilize a well-shielded planet, but enough to matter. Now layer on the starburst supernovae. Elevated supernova rates mean elevated cosmic ray flux. high-energy particles streaming through the galactic environment. Cosmic rays in a normal galaxy are already a significant source of background radiation. On Earth's surface, we experience about 2 to 3 millisieverts per year of natural background radiation, most of it from radon and rocks, with a smaller contribution from cosmic rays. Astronauts on the International Space Station, above most of Earth's protective atmosphere and magnetic field, receive around 150 millisieverts per year. That is roughly 30 times the ground-level dose, enough that NASA carefully limits astronaut careers to keep lifetime doses within safety guidelines. Now imagine a biosphere that, during the merger, sits inside a galaxy where the cosmic ray flux has risen by a factor of 10 or more, and where the central AGN is actively radiating, and where nearby supernovae are more frequent. That biosphere is not necessarily doomed, but it is a biosphere living in a fundamentally more hostile radiation environment than the one where terrestrial life has evolved for 4 billion years. Here is the domestic image I want you to hold. The atmosphere protecting you from the sun right now is thinner than the paint on a car when compared against the diameter of Earth. It is a fragile skin. The ozone layer that filters ultraviolet radiation is a small fraction of that skin. And that ozone layer is directly vulnerable to high-energy radiation events. Nearby supernovae, cosmic ray showers, gamma-ray bursts. The merger does not need to destroy Earth. It only needs to thin the paint. And a thinner atmosphere means more ultraviolet reaching the surface, means more DNA damage, means higher extinction pressure on complex organisms. Simple organisms in the oceans might survive. Land ecosystems, especially those dependent on photosynthesis and on ozone protection, would struggle. Now widen this. The habitability of a planet is not just about the star it orbits. It is also about the galactic neighborhood it happens to be in. Astronomers have started talking about a galactic habitable zone, a region of a galaxy where conditions are stable enough and radiation levels low enough for complex biospheres to develop. In a quiet spiral like the Milky Way, that zone is relatively large. In a starburst galaxy or an AGN-active galaxy, the zone shrinks dramatically. During the merger, the merged galaxy may go through phases where the galactic habitable zone essentially disappears, where no location in the galaxy is quiet enough, radiation-wise, to support long-lived complex life. This is the biology wall, the point at which the story stops being about physics in the abstract and becomes about the specific conditions that let complex organisms exist at all. Long before any stars collide, the environment that made you possible will have changed. Not because Earth was destroyed, not because the sun exploded, but because the galaxy around them shifted into a state that is fundamentally less hospitable to the fragile chemistry of life. And this is where I have to say something carefully, because the fairness matters. I'm not saying that biology is finished. I'm not saying that Earth will be sterilized. I'm not saying that life will end. Complex organisms are remarkably resilient, and life on Earth has survived catastrophes that seemed final at the time. What I am saying is that the merger creates a set of physical conditions that make continued biological complexity harder, not easier. And harder at the geological timescale means, on average, less of it. Less biosphere, less diversity, less complexity, fewer species, more frequent extinction events, a universe that trends in that region of that galaxy toward emptiness. The public story of Andromeda leaves this out entirely. It talks about the sky. It talks about the timeline. It never quite gets around to mentioning that the merger is, among other things, an extinction pressure. Not an immediate one. Not a single event one. A background pressure. A slow, sustained increase in the difficulty of being alive in that region of space. And that pressure, integrated over the hundreds of millions of years the merger will unfold, is enormous. But radiation is only the direct effect. The indirect one is what nobody in the press releases mentions. And that is where the story widens further. The direct effects of the merger, radiation, tidal disruption, starburst supernovae, are the obvious dangers. They are what any thoughtful reader would notice first if they looked past the reassuring summary. But there is a second layer of danger, and it may actually be more serious than the first. It is the disruption of the orbital architecture that made stable biospheres possible in the first place. Right now, the Sun orbits the center of the Milky Way in a relatively smooth ellipse, at a distance of roughly 26,000 light-years from the galactic center. The orbit takes about 230 million years to complete. Astronomers call that period a galactic year. In the entire history of Earth, the Sun has completed about 20 galactic years. In each of those years, the Sun has moved through slightly different galactic environments, sometimes closer to spiral arms, sometimes farther. But the orbit itself has been essentially stable. That stability is not a coincidence. It is the reason Earth's biosphere has had 4 billion years of relatively uninterrupted evolution. During a major merger, orbital stability degrades. The smooth ellipse of the Sun's path becomes chaotic. Not chaotic in the everyday sense of unpredictable weather. Chaotic in the technical dynamical sense, meaning small differences in initial conditions produce large differences in outcome, and the long-term behavior of the orbit cannot be reliably predicted. A chaotic galactic orbit can pass through regions of the galaxy that a stable orbit would never encounter. Denser regions, more radioactive regions, regions closer to active star-forming zones, regions closer to the galactic center. Every one of those passages is an environmental exposure, and exposures compound. A biosphere that would have been fine under any single exposure may not be fine under a sequence of them stacked across a chaotic orbital trajectory. Now widen the picture. It is not just the Sun that gets orbitally disrupted. It is also every other star nearby. During the merger, the density of close stellar encounters, stars passing within a few light years of each other, rises significantly. And close stellar encounters have consequences that most people never consider. Consider the Oort cloud. The Oort cloud is a vast, loose spherical shell of icy bodies surrounding the outer edge of our solar system, extending out to roughly 100,000 times the Earth-Sun distance. It contains an estimated trillion or more comets. Most of them sit there quietly for the entire life of the solar system, held loosely by the Sun's gravity, gently perturbed only by the tidal force of the galaxy itself and by the occasional passing star. When a star passes close to the Oort cloud, within a few light years, its gravity can perturb the orbits of a large number of comets, sending some of them plunging into the inner solar system. The Chicxulub impact, 66 million years ago, was the event that ended the age of the dinosaurs. Some researchers have argued that Chicxulub was caused by a comet, possibly perturbed out of the Oort cloud by exactly this kind of galactic encounter. That is speculative. The evidence is not conclusive, but the mechanism is real. Passing stars perturb the Oort cloud. Perturbed Oort cloud comets sometimes fall into the inner solar system. Some of those comets hit planets. During a merger, close stellar encounters become dramatically more common, which means Oort cloud perturbations become more frequent, which means comet showers become more likely, which means the impact rate on Earth-like planets rises, not by a small amount, by potentially an order of magnitude or more, sustained over the hundreds of millions of years the merger unfolds. Now stack the risks: elevated radiation, elevated supernova exposure, chaotic galactic orbits, frequent comet showers. Any single one of those, in isolation, might be survivable for a well-protected biosphere. In combination, they represent a sustained environmental assault that fundamentally changes the probability of long-term biological complexity. And here is what I mean by the merger being a structural problem, not a local one. The problems are not confined to the moment of maximum collision. They persist. The elevated supernova rate persists for hundreds of millions of years, until the merged galaxy settles into its new equilibrium. The chaotic orbits persist until dynamical friction slowly damps them out, which takes billions of years. The Oort cloud perturbations persist as long as the local stellar density remains elevated, which also takes billions of years. The AGN activity of the central black holes persists as long as they have material to feed on, which can be tens of millions of years or longer. So when we talk about the merger, we are not talking about an event. We are talking about a phase, a geological era of galactic environment change, during which the conditions that supported 4 billion years of biological complexity on Earth are progressively degraded. The event is not a moment. The event is a duration, and the duration is longer than the entire history of complex life on Earth. That is the logistics of a galaxy that does not stay put. It is not that the merger is scary because it happens quickly. It is scary because it happens slowly, sustainedly, across enough time that every buffer we depend on, orbital stability, low radiation background, quiet Oort cloud, quiet galactic center, gets eroded before the process is complete. And by the time the merged galaxy finally settles into its new elliptical shape, hundreds of millions to billions of years from now, the environmental conditions in that region of space will look nothing like the ones that produced us. This is the part where I have to be honest about what makes this story hard to communicate, because the timescales are so long and the effects so distributed that no single moment can be pointed to as the crisis. There is no dramatic instant of destruction. There is only a slow, cumulative degradation of conditions spread across timescales that dwarf human civilization. That is what makes the public framing so effective and also so misleading. It relies on the fact that the human imagination cannot easily hold a threat that unfolds over hundreds of millions of years. And so it presents the threat as if it were a distant singular event, when in reality it is neither. Let me turn now to something I've been circling around for the last several chapters, because it deserves to be named directly. The public story of the Milky Way-Andromeda merger is systematically softer than the physics warrants. That is not an accident. It is a product of 3 specific pressures that shape how large scientific institutions communicate with the public. And I want to walk through those pressures carefully, because the point is not that scientists are lying. The point is that the summary is doing PR work the papers are not doing. The first pressure is timeline dilution. When a story has a timeline of 4.5 billion years, it becomes emotionally trivial for most listeners. 4.5 billion years is longer than the current age of Earth. It is longer than the age of any known biological process. It is a number so large that human beings essentially cannot feel it as a threat. So when an institution communicates the merger as a 4.5 billion year event, the timeline itself does most of the reassuring work. The public hears the number and mentally shelves the story as not relevant to me or to anyone I will ever know. But the timeline is a specific choice. It is the moment when the visible galactic disks begin to interpenetrate. It is not the moment when the interaction begins. As we have already discussed, the halos are already in contact. The gas is already sloshing. The gravitational influence has been ongoing for hundreds of millions of years. The 4.5 billion year figure is technically correct for one specific phase of the merger, and it is presented as if it were the whole story. The rhetorical effect is to make an ongoing process sound like a distant event. That is not a lie. That is a compression of the truth that changes its emotional weight. The second pressure is funding narrative. Space science, astronomy, astrophysics. These are fields that depend heavily on public support for continued funding. Telescopes cost billions of dollars. Space missions cost billions more. Sustained public interest is essential to justifying those expenditures to legislatures and taxpayers. And sustained public interest in the modern communication environment is driven by wonder, curiosity, and inspiration. Dread does not fund telescopes. Wonder funds telescopes. So when institutions communicate the merger, they naturally emphasize the wonder, the beauty of the two galaxies drifting together, the magnificent new object that will emerge, the privilege of being alive to think about such vast cosmic dramas. All of that is genuine. All of that is real. But it is also the framing that best supports continued funding. And so the framing tilts, subtly and systemically, toward wonder and away from warning. The third pressure is public psychology. No stars will collide is a rhetorical layup. It is a memorable, quotable, factually accurate line that ends the conversation before harder questions can be asked. It is the kind of soundbite that travels well on social media and in short news segments. And it functions, whether intentionally or not, to redirect attention away from the actual mechanisms of the merger: tidal disruption, starburst supernovae, AGN activation, orbital chaos, and toward a question that has an easy, reassuring answer. None of this means anyone is lying. I want to be very careful here. The physics I have been describing throughout this piece, the halo overlap, the dark matter dominance, the tidal disruption, the starburst supernova, the AGN activation, the orbital chaos, all of that is in the peer-reviewed literature. It is not hidden. It is not secret. Any astronomer working on galactic dynamics can walk you through it in detail. The information is available to anyone who wants to look. The problem is that most people do not want to look. They read the press releases, they watch the documentaries, they accept the softened summary as the full story. And the softened summary is not doing them a favor. It is preserving their comfort at the cost of their understanding. Because the papers are darker than the summaries. The papers describe a violent, prolonged, structurally destructive event that reshapes both galaxies and produces a fundamentally different kind of object in their place. The summaries describe a gentle merger. Both are, in a technical sense, true, but they are not equivalently informative. Here is my fairness clause, and I want to state it plainly. I am not saying scientists are hiding anything. I am not saying there is a conspiracy. I am not saying the public should distrust astronomical institutions. What I am saying is that the way large scientific findings get translated for public consumption is shaped by pressures that systematically favor reassurance over accuracy in one specific direction, toward less alarm, toward more wonder, toward comfort over confrontation. That is a real pattern, and it is worth naming. And the specific human consequence of that pattern is this. Most people alive today have never been told, in language they could actually feel, that the merger between the Milky Way and Andromeda is not a distant future event, but an ongoing process. Most people do not know that the halos are already in contact. Most people do not know that our own predictions of the merger have been consistently revised toward closer, sooner, larger, and more consequential. Most people do not know that the eventual merged galaxy is not a bigger Milky Way, but a different kind of object entirely. Most people do not know that our solar system has a non-trivial chance of being ejected and a larger chance of being pulled inward toward the merging cores. Most people have been given the wonder version, and only the wonder version, because the wonder version is what supports the institutional communication model. And this is the point where I want to strip away the softening entirely. Because once you strip it away, Andromeda stops being a beautiful spiral in the night sky. It stops being a distant future curiosity. It stops being a philosophical thought experiment about deep time. And it starts being what the physics actually describes, which is the largest gravitational structure in our part of the universe, closing on us at 250,000 miles per hour, already touching us at the edges, and set to fundamentally reshape the conditions of the region of space we depend on for our survival. That is the story. And once you see it that way, you cannot really see it the other way again. I have spent the last 8 chapters talking about Andromeda as if it were the whole story. It is not. It is the largest and most immediate part of the story. But it is not the whole story. And the whole story, when you finally see it, is bigger and stranger than the merger alone. Andromeda is a symptom, not the disease. The disease, if that is even the right word for it, is a process that has been unfolding since the earliest history of the universe, and that we are only now beginning to understand well enough to describe. The local group, the small cluster of galaxies to which we and Andromeda both belong, is not a random collection of neighbors. It is a gravitationally bound structure, which means everything in it is falling toward everything else, and has been for billions of years. The local group contains about 80 known galaxies. 2 of them are large, us and Andromeda. One is medium-sized, the Triangulum Galaxy, also known as M33, which sits at a distance of about 2.7 million light-years and is itself gravitationally bound to Andromeda. The rest are dwarf galaxies, small satellites orbiting one or the other of the two major systems. All of them are moving under mutual gravity. All of them are, in the long run, converging. The merger between the Milky Way and Andromeda is only the first major event in that long convergence. After the merger, M33 will most likely fall in as well, adding its own mass to the combined system. The dwarf galaxies will continue to orbit and eventually spiral in. Over tens of billions of years, everything in the local group will end up in a single, unified, elliptical galaxy. That is not a speculative prediction, that is what happens to gravitationally bound systems, and even that is not the end of the story. Because the local group itself is not isolated, it is one of many galaxy groups within a much larger structure called the Virgo supercluster. And the Virgo supercluster is not isolated either. It is part of an even larger flow of matter, drawn toward a mysterious region of the universe called the Great Attractor, which sits behind the plane of our own galaxy, in a direction that has been notoriously difficult to observe. Every galaxy in our neighborhood, every group, every cluster, all of it is falling on some timescale toward destinations set by the large-scale gravitational structure of the universe. Let me reclassify what we have been talking about. What I described in the first 8 chapters as the Milky Way-Andromeda merger is really something bigger than that. It is one visible episode in the ongoing process of the universe's large-scale structure resolving itself. Galaxies merge, groups consolidate, clusters form, and on the largest scales, matter flows toward gravitational wells that were set in place in the earliest moments after the Big Bang. The merger is not a special event. It is a local instance of a universal process. What is unusual is not that it is happening. What is unusual is that we happen to be inside one of the pieces getting resolved. That framing matters, because it changes what the merger means. If Andromeda were just a one-off event, a fluke, a random collision, an unlucky alignment, then it would be easier to think about as an isolated future crisis. But it is not. It is a preview. It is what happens when gravitationally bound structures do what gravitationally bound structures do, and it is not going to stop after Andromeda arrives. There will be M33, there will be further consolidation, there will be eventually the fall of the entire local group into whatever larger structure it is being drawn toward. Which means the stability we experience right now, the specific, remarkable, quiet gravitational environment that allowed 4 billion years of unbroken biological evolution on Earth, is not the natural state of the universe. It is a temporary local condition inside a larger, more violent process. We happen to evolve during a quiet interval, not a permanent one, an interval, and the interval is ending. Now think about the trend line I mentioned earlier. Every prediction we have made about Andromeda over the last 30 years has been revised in one direction, toward more mass, toward more transverse motion, toward larger halo extent, toward earlier interaction, toward more consequential outcomes. That trend line is telling. It is telling us that our understanding has been consistently conservative, that the physical reality has, in every measurement, been more serious than the prior expectation. And that pattern is not unique to Andromeda. It is a pattern we see across many domains of astronomical research. Dark matter turned out to be more abundant than early estimates. Supermassive black holes turned out to be more common. Galaxy mergers turned out to be more frequent in the universe's history. Cosmic ray flux turned out to be higher in starburst environments. In area after area, the universe has revealed itself to be more dynamic, more energetic, and more consequential than the previous generation of astronomers believed, which raises an uncomfortable question. If our understanding has been consistently conservative, if reality has, at every step, turned out to be more intense than we thought, then what is our current understanding of Andromeda still getting wrong in the direction of underestimation? I do not know the answer to that question. Nobody does. That is the nature of a moving frontier of knowledge. But if you take the trend line seriously, you have to entertain the possibility that the merger is closer, larger, or more consequential than even our current models predict. Not by a factor of 2, not by a factor of 10, but by some amount, in some direction. And that amount, whatever it is not going to be revised toward less serious. It never has been. It probably will not be now. So this is the widest frame. Andromeda is not just an approaching galaxy. It is a symptom of the universe's large-scale gravitational architecture. That architecture has been driving structure formation for 13 billion years, and it will continue to drive structure formation for tens of billions more. The merger is one moment in a much longer process, and the stability we take for granted, the quiet sky, the stable orbit, the low radiation, the well-behaved neighborhood, is a temporary artifact of the particular moment we happen to live in. Which brings us back to the beginning, and to the sentence nobody wants to say clearly. Here is the verdict, and I want to state it carefully, because I have spent 9 chapters building the case, and this chapter has to consolidate it without softening it. Andromeda is not a galaxy in the way the public uses the word. Not really. It is a gravitational structure whose visible stars represent about 15% of its total mass. The other 85% is dark, invisible, unmapped in detail, and dominant in determining what happens to us. Its true extent, measured by its halo, is roughly 6 times wider than the full moon in the night sky, if we could see it. Its closing velocity is roughly 250,000 miles per hour. Its outer envelope is already in contact with ours. The event most people think of as in the far future has, at the halo level, already begun. The merger will not gently combine 2 galaxies. It will end both of them. What emerges on the other side, hundreds of millions to billions of years from now, is not a larger Milky Way. It is a different kind of object entirely. A featureless elliptical galaxy whose formation is defined by tidal disruption, black hole coalescence, starburst-driven supernova cascades, and the loss of the spiral structure that gives our night sky its familiar shape. The band of stars we call the Milky Way, the pattern that has organized every human sky for the entire history of our species, will not survive. Our solar system has, by some models, a roughly 12% chance of being ejected from the merged galaxy entirely. That sounds bad. It is not the worst case. The worst case is the opposite. Being pulled inward, closer to the merging cores, closer to the black holes, closer to the starburst regions, closer to the AGN radiation. The median outcome is not exile. The median outcome is proximity to the disturbance. And the disturbance itself, once it fully develops, is not a moment. It is a phase. A geological era of galactic environment change during which the specific conditions that supported 4 billion years of biological complexity on Earth are progressively degraded. Elevated radiation, elevated supernova rates, chaotic orbits, more frequent comet showers, reduced size of the galactic habitable zone. None of these effects sterilize Earth. All of them make the biosphere harder to sustain over long enough timescales for complex organisms. The comforting phrase, "no stars will collide," is true. And beside the point. Stars are not what matters. What matters is the shell of gas and gravity and magnetic field and radiation environment that lets a rock like Earth grow forests instead of remaining a sterile ball of stone. That shell is fragile, and the merger, at its peak, is exactly the kind of process that erodes fragile shells. Now let me return to the beginning, to the smudge in the night sky, to the object that everyone has been trained to think of as beautiful, distant, and safely irrelevant. That smudge is not a beautiful, distant, safely irrelevant object. It is the leading edge of the largest gravitational structure in our part of the universe. It is already touching us. It is closing on us. And it is going to reshape the environment that produced us on a timescale that dwarfs human history, but that is nothing compared to the age of the universe. The reason the public story has been so gentle is not that the physics is gentle. The physics is not gentle. The physics is dramatic, sustained, and structurally consequential. The reason the public story is gentle is that gentleness is easier to communicate, easier to fund, and easier to live with. But the gentleness is a translation choice. It is not the underlying truth. Now let me offer the narrow hope, because the fairness clause requires it, and because I believe it. The timeline gives us time. 4.5 billion years to the disk-level interaction is a lot of time. If our species, or whatever our species becomes, lasts even a small fraction of that timeline, we will have hundreds of millions of years to understand the merger, prepare for it, and if necessary, leave the vicinity before the biosphere is too degraded to support us. That is a real possibility. It is not the current plan. But it is a possibility. The catch is that possibility only matters if we understand what we are dealing with. And we cannot understand what we are dealing with if we keep telling ourselves the softer version of the story. The softer version, the one about the gentle merger and the beautiful new galaxy and the 4.5 billion year distance, is a story that lets us not think about the problem. Which is fine for now. But it will not help us later when the problem needs to be addressed. So the point of this piece is not to alarm you. The point is to reframe. To take the picture you have in your head of Andromeda as a distant, beautiful spiral and replace it with something closer to what the physics actually describes. A gravitational structure that is mostly invisible. A closing velocity that would carry it across the diameter of Earth in 1/3 of a minute. A halo that is already touching ours. A merger that has, at some level, already begun. A future that involves tidal disruption, active black holes, starburst supernovae, chaotic orbits, and the eventual erasure of the disk we live in. I am not saying you should be afraid tonight. Nothing about your life today is going to change because of Andromeda. Your children's lives will not change. Your grandchildren's lives will not change. The timescales are too long for that. What I am saying is that when you look up at that pale smudge in the constellation Andromeda, the one you can see with your naked eye on a dark night, the one every astronomy book calls beautiful, you should know what you are looking at. You are not looking at a peaceful neighbor. You are not looking at a distant curiosity. You are looking at the leading edge of the largest object in our part of the universe. It is coming. And the story of what it actually is has been softened for a long time by people who meant well, but who chose comfort over clarity. Andromeda is not a galaxy. It is what is about to happen to ours.